So today we're going to take a look at section 8.3, and section 8.3 begins on page 565. Now we're going to talk about graphing general rational functions. So in the last lesson we were graphing simple rational functions. Those are the ones that always had one vertical asymptote, one horizontal asymptote, and always give you a two-piece graph, a hyperbola, with two branches on it. So now we're going to talk about graphing general rational functions. We don't know ahead of time how many vertical asymptotes or horizontal asymptotes we're going to have. We may have no vertical asymptotes, we may have one, we may have two. On the horizontal asymptotes, we may have none, we may have one. So we have a number of different possibilities, each of which leads to a different shape for our graph. And so that's why these are general ones rather than simple ones. They're just not predictable like the last ones. But as far as working with them, we're going to do exactly the same math to them to graph them that we did with the simple ones. There just may be a few extra points to plug in. So let's take a look at our first example, which is going to be example 1 on 565, y equals 6 over x squared plus 1. Now, this is one that gets people into trouble all the time because they don't pay attention to what they're doing. The first thing we always want to do is we always want to start by finding our vertical asymptote. And to find our vertical asymptote, we take the denominator, x squared plus 1, and we set it equal to 0 and solve for x. Well, we're going to subtract 1 from both sides, which gives us x squared equals negative 1, not positive 1. And so now, if we square root both sides, we have to put plus or minus in. And so we end up with x is equal to plus or minus the square root of negative 1, which gives us an I. The problem is when we draw an xy graph in the real plane, I does not show up anywhere, which means that there are no vertical asymptotes. What that means is that there's nothing to break our graph apart into separate pieces. Therefore, this will be a one-piece graph. Now, as far as the horizontal asymptote goes, we again use the three-part rule. We look for the highest power of x, which is in the denominator on the bottom, and so therefore our horizontal asymptote is y equals 0. So when I go to graph this, let me get my graph grid here. So there's no vertical asymptote to put in, but there is a horizontal asymptote at y equals 0. So let me put that in. Make sure you draw that in. It's very important. Now, since there is no vertical asymptote, there's no left side, there's no right side, there's no middle, what I'm going to do is I'm just going to plug in the following numbers on my t-chart. And this is what I would always plug in when you have the one-piece graph on these. I would plug in 0 in the middle, 1, 2, 3, negative 1, negative 2, negative 3. Don't just go 0, 1, 2, negative 1, negative 2, because it won't quite give you enough of the picture to get the curvature looking good. Okay, when I plug in a 3 here, I get 6 on the top, and I get 3 squared is 9 plus 1, which is 10 on the bottom. That gives us 0.6 if you punch it into your calculator. If you plug a 2 in, you get 6 over 4 plus 1, which is 6 over 5. That's 1 1/5, or 1.2. When you plug in a 1, you get 6 divided by 2, which is 3. When you plug in a 0, you get 6 divided by 1, which is 6. If I plug in a negative 1 squared is 1, so I get 6 over 2, which is 3 again. If I plug in negative 2 squared is 4. 4 plus 1 is 5, so we get 6 over 5, or 1.2 again. And this one gives us 0.6 again, 6 over 9 plus 1. So now when I go to graph this, I have 0, 6, which is up here. I have 1, 3. I have negative 1, 3. I have 2, 1.2, about there. Negative 2, 1.2. And 3, 0.6 is about there. Don't forget that this thing is going to zero in on its horizontal asymptote. Now, very important, this has to be rounded at the top. It does not come to a point. This is not a V. What this is a bell-shaped curve. Some teachers refer to that as a bump graph. You can call it whatever you like, but this is what it looks like. If there was a negative in front of the 6, then these would have all been negative, and this thing would have been bumping down, so to speak. Now, if we take a look at domain and range are not going to be predictable. We're going to have to look at the graph. So if I connect this thing to the x-axis, notice that this will cover the entire x-axis forever. So that's going to be all real numbers on this one, but you have to check and see. It's not predictable. Now, on the range, we're going to connect to the y-axis. Well, notice if I connect these to the y-axis, what I end up getting is I end up getting everything on the y-axis except for 0. And notice I also don't get anything above 6 or below 0. So what we're getting is we're getting y values that are greater than 0 but less than or equal to 6, because we do actually get 6 right there. But nothing at 0 or below, so y greater than 0. Nothing above 6, but we do get at 6. All right, let's take a look at one more example, a slightly more involved example, but it's not more difficult. There's just more points to plug in, and that's going to be our three-piece graph. And so let's take a look at y is equal to, and let's do 2x squared over x squared minus 9. So we're going to start this the same way we start all of them. The first thing we're going to do is we're going to find the vertical asymptote by setting the denominator equal to 0. Well, if you add 9 to both sides, you get x squared equals 9. And then you square root both sides with plus or minus, and you get x is equal to plus or minus 3. So x equals positive 3 and x equals negative 3 are going to be our two asymptotes, our vertical asymptotes. So on this one, it's a little bit different than what we've seen so far. We have a vertical asymptote at x equals positive 3. But we also this time have a vertical asymptote at x equals negative 3. Now, as far as the horizontal asymptote goes, we look to see where the highest power of x is. Notice that we have x squared as the highest power on the top and x squared as the highest power on the bottom. Those are the same, so what you do is you ignore anything else and you just take a look at those two terms. 2x squared divided by x squared is going to give us, just get rid of those, y is equal to positive 2. So this ends up being our horizontal asymptote. Now notice on this one that what has happened is we have two vertical asymptotes, which has cut our graph into 1, 2, 3 pieces. We have a left, we have a middle, we have a right. So I'm going to break my t-chart into a left, a middle, and a right. On the left side, I'm going to plug in the first three numbers to the left, which would be negative 4, negative 5, negative 6. In the middle, I'm going to plug in negative 1, 0, and 1. On the right side, I'm going to plug in 4, 5, and 6. Okay? Now, again, feel free to use your calculator to help you do this thing. So, if I plug in negative 4 squared is 16 times 2 is 32 over negative 4 squared is 16 minus 9 is 7. So you end up with 32 divided by 7. If I pull my calculator up, 32 divided by 7 gives us an answer of about 4.6. I plug in negative 5, I get 25 times 2 is 50. Divided by 25 minus 16 is, 25 minus 9 is 16. 50 divided by 16 gives us about 3.1. If I plug in negative 6, I get 36 times 2 is 72 on the top. I get 36 minus 9 is 27 on the bottom. 72 divided by 27 gives us about 2.7. So there's the left piece. I'm going to graph that now. Negative 4, 4.6. Negative 5, 3.1. Negative 6, 2.7. Notice this thing is behaving exactly the way we would expect if this was one of our two-piece graphs. It's hugging its asymptotes, and this is what you get. Now I'm going to skip down to the bottom. Notice that the numbers I'm going to plug in I'm plugging in for x's that are all being squared, which means it doesn't matter if I plug in a -4 or a +4. If I plug in a +4, I still get 16 times 2 is 32 on the top, and I still get 16 minus 9 is 7 on the bottom, so that means I'm still going to get positive 4.6, positive 3.1, positive 2.7. Okay, don't just assume that it's going to give you the same numbers. This one happens to, but you do need to check them. I'm just going to save us a little bit of time so you don't have to spend as much time watching the video. You can verify for yourself that those are in fact the points that we get. And so this one goes like this. Okay? So it looks similar to a hyperbola, but not really. It does give us two branches. Now we're going to come to the middle, and the middle is where things can get tricky. But let's start by plugging these in. If I plug in 0, I get 0 over -9, which is 0. If I plug in 1, I get 2 over -8, which is -1/4, or -0.25. If I plug in -1, I also get 2 over -8, which is -0.25. And so what I get is 0, 0. I get 1, -1/4, -1, -1/4. And what it looks like this thing is going to do is it looks as if this thing is going to go like this. Kind of like a parabola, although it cannot be a parabola because parabolas don't have asymptotes. This one does. But it has that kind of look to it. Now, the question is that really what this one is doing? Because the problem is that sometimes what these will do is they'll go down for a while on one side, and then they'll reverse direction and shoot up. We don't know for sure, but there's a way we can be a little more sure. And on these three-piece graphs, my recommendation is you always test 2 additional points. You don't have to necessarily graph them, but you need to test them. Go 1/10 inside of the right asymptote. So instead of 3, we're going to go 2.9 right about here. And go 1/10 inside the other asymptote. In this case, that'll be -2.9. We're going to plug these numbers in just to see what we get, just for the fun of it. So if I plug in 2.9, I get 2 times 2.9 squared. So 2 times 2.9 squared gives us 16.82 on the top. On the bottom, I get 2.9 squared minus 9 gives us -0.59 on the bottom. And if we do the top divided by the bottom, -0.59, notice we get a rather large negative number, -28.5. This one, when you plug it in, is also going to give you -28.5. Notice if I go to here, I have to go all the way down to -28.5 down on the floor somewhere. So obviously this thing is going to keep going down. So you don't have to graph those last 2 points. You just want to plug them in to see. If it had given you a positive number, then we would have known that this goes for a while and then turns around and then shoots back up. Now, this is our final graph. But if it had turned around to shoot back up, notice what would have happened is this would have eventually crossed its horizontal asymptote. So let me talk about the horizontal asymptotes for a moment. Understand that vertical asymptotes are etched in stone. They cannot ever be touched under any circumstances by your graph. Because what creates the vertical asymptote is where the denominator is 0. If we take a number divided by 0, we don't get a y-coordinate. Therefore, there's no point that we can put anywhere because there's no y-coordinate for it to go on. Horizontal asymptotes don't work that way. Horizontal asymptotes are derived. That 3-part rule is derived by using end behavior that we studied first semester. What happens when you plug in a really, really huge positive number out here or a really, really huge negative number out here? Well, we know this thing is going to approach y equals 2. So it's going to get closer and closer going this way. It's going to get closer and closer going this way. What that does not do is tell us what happens for small values of x. We have no idea what goes on in here, which means that it is possible that your graph could bump your horizontal asymptote somewhere in the middle here. So if this did turn around and shoot back up, then what you would do is you would check your numbers, and if it really does that, then you would go ahead and make it turn around and shoot back up, and it would cross its horizontal asymptote, but it will not ever touch the vertical one. All right. So that covers that issue. Now, the last thing that I want to talk about here is domain and range on this problem. Domain on this problem, notice if I connect this to the x-axis, it goes forever that way. And if I connect this to the x-axis, it goes forever this way. And notice if I connect this to the x-axis, it just stays in between those two. Notice I get the whole x-axis except for -3 and +3. So it's going to be x cannot equal 3 or -3. Or you could just write it this way if you prefer, x cannot equal + or -3. Either one is acceptable. Range is a little trickier. So let me grab these and get rid of them so they're not in our way to confuse the issue. If I connect these to the y-axis, notice that this one connects in here forever, going upward. This one connects in here forever, going upward. This one connects here, going downward forever. Notice that we have a big gap in here. We get the whole y-axis except for this gap. Notice it's in two distinct separate pieces, which means you have to write your range in two distinct separate pieces. Either y is less than or equal to 0, that's this piece, or, and you have to put the word or in there, y can be bigger than 2. So you just do them each separately as if that was the whole range, and you just connect them with the word or. That's what happens if your range, or if your domain in that case, is in two pieces. You can write them separately. Now, our domain was actually 3 pieces, but we could take care of it just by writing what it's not, because it wasn't a big gap. It was just one particular break. Okay, so that's how that works. So the other possibility I'm not going to do an example of, but you can see in your book example number 3 what happens when you end up with what is called an oblique or diagonal asymptote. This happens when the highest power on the top is 1 higher than the highest power on the bottom. If this guy is 1 degree higher than that, then you're going to get a diagonal asymptote because there's no horizontal asymptote on this because the highest power is on the top. But it's 1 degree higher, it turns out it gives you a diagonal asymptote, and so what ends up happening is wherever your vertical is, you end up with a diagonal asymptote, and what it does is it causes your graph to look like this. It hugs both asymptotes, and it gives you this weird diagonal. If you start to plug in your points when there's no horizontal asymptote, and you start to see this thing curve up and curve down like that, even though there's no asymptote here to zoom in on, then chances are you probably have an oblique asymptote. This is something you deal with a little bit more in math analysis. We're not going to worry about it too much in here. Okay, that's it for the lesson.